program throughout the.
Yeah. Man, I still like the good old-fashioned roller coasters, you know? But that was a pretty cool experience. All right. We had fast passes, so you know the way they do it now, you get 3 fast passes a day, and then once you use them up, you can start getting fast passes. But that particular, no, you know what? Yeah, we have fast passes for that. It's always like 2 hours or longer. Yeah, so we only rode it one time because we didn't want to wait again. But there was another ride over in Universal. Is it Universal? No, Planet Hollywood. No, Hollywood Studios. Yeah. That's Disney, right? Yes. Yeah. So there was they had a new roller coaster called Slinky Dog, and it's for like smaller kids. Awesome roller coaster though. Super smooth and enough to make it worth it. But that we didn't have fast pass for. We waited an hour for that one twice. So it was good. Yeah, it's crazy. All right, everyone, how are y'all doing? You ready? All right. So last class we had introduced polar coordinates, right? And I think I ended the class. I proved that the area of a circle is pi r squared using that very nice formula that the double integral over d, where your integrand is 1, gives you the area of the region you're integrating over. And that's how I proved that the area of a circle is pi r squared. I believe we did this problem. Is that correct? Double check your notes. Or we did this one. We did this one, sorry. We did that one. I don't remember if I showed you the picture of this. I don't think I did, and that's why I wanted to bring it up. We set up the integral for this, but the actual picture was, we had this surface. We were trying to find the volume under it, but our region of integration was the region between these 2 circles, or between these 2 cylinders, which came out to be 2 circles on the ground. So I just wanted us to look at this again, just visually. So this was the region we had on the ground, and we were taking just those points and pushing them up into the surface, and then trying to find the volume below it. So here's the region on the ground. You can see it. Here's the surface, and then the black points here are just the edges of that circular region. And then the solid we're trying to find the volume of is right there, and I'll have to take everything else out of here. So you can kind of see it. See that solid there? We were trying to find a formula for the volume of that, which we did. Notice also that some of that volume, some of that solid is going to be below the XY plane, so that would have counted as negative volume. So we're getting, again, like the net volume. So that's what we did. And now we're going to do this one here. We did not do this, right? Okay, so this one, we're trying to find the volume bounded by some paraboloid, z equals 4 minus x squared minus y squared, and the xy plane. So what is the volume of the solid bounded between these two? Now, there's nothing that tells us we need to use polar coordinates here. Nothing at all, right? There's no indication that we should use polar coordinates. So what we want to start with maybe is getting an idea of what this looks like, and I'm just not quite sure how comfortable you are with that part of it yet. That's just going to depend on you. One thing we could do is try and visualize what happens here. What happens if we just start plugging in the point 0, 0, right? We plug in 0, 0, what do we get? 4. So up on our z-axis, we'd be up here at 4. And then What if z is 0? If z is 0, that means we're down on the ground, right? And what would that look like if z is 0? Yeah, we would have this, and if we move the x squared and y squared over to the other side, we'd have that, right? And that would be a circle on the ground of radius 2. So we know that those points live on the paraboloid, and we're trying to find the volume of the solid bounded by the xy plane, which is the ground, and then the paraboloid, which it looks like, I don't know, are y'all okay with the idea that this is just this shape, like that? Okay. So this goes back to chapter 10 when we did the quadratic surfaces. We want to have some idea of what these things look like, right? Because it helps us here. All right, so do y'all see the solid we're trying to find? The volume of right here? It's above the xy plane and below this paraboloid. So in terms of the double integral, we need to have like a top surface and a bottom surface. So what would our top surface be? And I'll call it f of xy here. What would that be? And then what would our bottom surface be? G of xy.
F of xy is the 4 minus x squared minus y squared?
Yeah, it's just this solved for z. So it's the paraboloid. And then the ground, right, is z is 0. All right? So we need to now figure out what are our limits of integration going to be, right? What are our limits of integration? And that's when I was, telling you last class or the class before, if you were to shine a light from here straight down and you look at, the shadow of this object on the ground, on the xy plane, well, you really wouldn't have a shadow because it's touching, right? But it makes that circle, right? So that is our domain, is that circle on the ground. So in terms of D, our domain, in the xy plane, it's just a circle of radius 2. So that is D right there, right? And when it comes to double integrals, that region is perfectly suited for polar coordinates, right? I mean, that's the type of thing that we like to use polar coordinates for, circles or circular regions. So if I were to try and come up with some sort of restrictions on theta and r in polar coordinates, then how could I draw that region? What restrictions would I have on theta? 0 all the way around to 2 pi? Okay. And then what about my radius? 0 to 2. So that means you're going to do all points with radius 0 to 2, but you're going to swing around all the way, and that will cover the whole region, right? I've had students in the past ask me this question. Would this have worked? Would this have worked for our region instead? So think about this. You start here, right? And you always start by pointing out the x-axis. So we're pointing that direction. And I'm allowed, my radius is going to be from where to where? Negative 2 to 2. So that means I'm going to go out to 2, but then I'm also going to go backwards. So it would cover like that line and that line, right? But then I'm going to rotate a little bit and do it again. And keep rotating, but I'm only going to rotate through to pi. Do y'all see why I'm only going to go to pi? Right? Because once I get, like if I were to rotate just from here to here, I would get everything there and everything behind it, like right over here. Right? So as I keep going, once I get halfway around, I will have covered the whole circle. So you can, but we normally like to keep our radius positive, but it doesn't have to be, because our radius you think positive. But it's really just telling you, which how far to walk out. Positive is that way and negative is that way. All right. So I'm not going to do this. I just want to bring that up. All right. So we've got our region, and so what we're going to do is we're going to set up this double integral. We're going to go double integral over D. We're going to do f of xy minus g of xy with respect to area. But we're going to convert this to polar, right? So we're going to take this, convert it to polar coordinates. And when we do that, let's see what happens. So maybe I'll just, well, I'll leave those there. I don't need this. Okay. So when I do that, I'm going to have a double integral. I'll put my limits of integration on in just a second, all right? So what is f of xy going to become? Remember, it has to turn into things with r and theta, right?
Cosine theta?
So everywhere we see x, it becomes our cosine theta. Everywhere we see y, it becomes our sine theta. So let me write out one more line. Remember, this is going to become f of r cosine theta, r sine theta, minus g of r cosine theta, r sine theta. And then once we go to polar, we have this, well, we'll call it dA still, right? So what would happen if I come to the f function, I replace x with r cosine theta and y with r sine theta? Let's see. So f of r cosine theta. You might see this already, what's going to happen. Well, maybe I'll do a shortcut. Do you all agree that this is this? Do you all agree that that's that? But what is x squared plus y squared? Back when you were doing from Cartesian over to polar, there were some important relationships. It's r squared, right? It's r squared. Now you could have gotten it. Okay, let me show you how you could have gotten this. If you just replace that there, you would have got r squared cosine squared theta, then minus r squared sine squared theta. And then you could have factored out a negative r squared out of both of those, and you would have been left with cosine squared theta plus sine squared theta, and that's 1, right? So this right here, you would have got to the same place as here, 4 minus r squared. But that's shorter, isn't it? Okay, so I'm going to go 4 minus r squared. So I'll be replacing this with 4 minus r squared. This will be what? Well, the g function is just 0, so that's just going to be 0, so that's not going to be there. I'm going to replace dA with what? R dr d theta, or I could go r d theta dr. It doesn't matter which order I go, because these are both constants, so that doesn't matter. You following? All right, so here I'm going to continue. I'm ready to go from here to the next line, which is double integral. I'll put my limits of integration on here in a second. 4 minus r squared. Okay, that's this part. And then r, and then I guess I'll go dr d theta. And that means that my theta is on the outside, 0 to 2 pi, and my radius is 0 to 2. That's my inside. And this is it. This is the integral. This is a pretty simple integral, isn't it? I mean, just distribute the r through, and then just use your power rule. And everything should work out pretty clean. We'll get an answer just so we have one. So if you go do this on your own.
You said the last time that the order doesn't matter, right?
The order doesn't matter because they're constants. We're going to see here in a moment that we'll have a problem where they aren't constants, where one of them is not constant, and therefore the order will matter. But if they're both constants, this is actually just like the rectangular. Like when we did our first double integrals, before we did type 1 and type 2, we integrated over a rectangular region. And in that case, we could switch the order. Same thing here. You can't get rid of the r, though. The r's got to stay there. Zero to 2. And we're doing, I'll go ahead and distribute now. 4r minus r cubed. And we're integrating with respect to r, then theta, I'll just put t. 8 pi. So the volume underneath that paraboloid, or between that paraboloid and the xy plane, is 8 pi. I would expect that you could do that by hand. That's a pretty clean one. Questions on that? It's all right? Okay, let's look at this next one, or the next idea here. So you know how, yeah, we just kind of did this, the volume between two surfaces. I mean, that's what we really did, right? We had two surfaces, except one of them was the ground. This formula right here is just reminding us that it doesn't have to be the ground. So this bottom surface could be some function of x and y, which we may have to convert over. Okay, so we may have a region on the ground that's polar. We may have a top surface and a bottom surface. This one will be converted over, f of r cosine theta, r sine theta. And the bottom one is just like we just did, but doesn't have to be trivial. Last one was 0. This next example, it's not going to be 0. So find the volume between, oh, we didn't look at the picture of the last one. We have to look at the pictures because what's the point of me writing the code to draw the picture if we don't have the picture? There we go. So that was it. There's our domain on the ground. Here's the paraboloid. There it is. Okay, and we're trying to find the volume between them, which is just basically that dome right there, right? We just found the volume of that. It's 8 pi. All right, find the volume between the volume of the solid below this. What is that? Sphere of radius 1. So when we say below, maybe I should have said inside, okay? So we have a sphere of radius 1. I want the volume below that and above this cone. So we know this is a sphere of radius 1. This is a cone that would look like this, right? Like this right here is a cone, looks like that. How do I know it looks like that? Well, this actually comes from this equation. That's me squaring both sides. And if you go back and you look at the formulas for quadratic surfaces, this is the formula of a cone that goes like that. The cones actually go open up like that and down. But when we take the square root on both sides, we could have done a plus or a minus here. The plus gives us the top part of the cone, the minus gives us the bottom part of the cone. So we are looking at just the top half. Does that make sense? You could also just plug in some points. Again, like if you took the xy plane, or xyz, you plug in 0, 0 for x and y, right? You would get 0, 0, you get z is 0. And then, I don't know, let's pick a value up here for z, like, let's go with 3. So what would it look like at z equals 3? If I replace that with 3, then you square both sides, right? So if I replace that with 3, square both sides, I get 9 equals x squared plus y squared, which should be a circle, right? So I should have a circle up there. And then the bigger z gets, the bigger the circle gets. So you get that cone. Make sense? All right, so we've got a cone and we've got a sphere. So that's the picture of it right there. And we're trying to find the volume of the solid that is below the sphere, or we just said inside the sphere, and above the cone. It's everything inside the sphere and everything above the cone. So when we say above the cone, we mean, you know, that cone. Yeah, it's kind of like this is outside the cone, right? This is outside the cone? No? That would be below the cone, though, because the cone extends forever, doesn't it? So if I'm a point over here, then I am below the cone. If I'm a point up here, then I am above the cone. So I want basically the solid above the cone and below or inside the sphere. So we're looking at this solid here, which I will have to pull out the cone and pull the cone. I'll leave it there just a little bit, and I'll pull the sphere out just a little bit. And so you've got that solid inside there. See that? That's a snow cone, right? It's a little snow cone. We want to find the volume of that snow cone. All right, so do we have a top surface? I'm going to do this. I'm going to draw this myself. The computer's kind of cheating because you don't have the ability to draw it like that. So I'm just going to draw it like this. I have the top part of the snow cone like this. This is what I'm trying to do, right? Trying to find the volume of this thing. I have a top surface, don't I? The top surface is the sphere, right? And the sphere, I have to solve it for z in order to look at it as a function of x and y. So solved for z, this would be what? Yeah, square root, right? Because you're going to have to take square root. And then 1 minus x squared minus y squared minus, sorry, I don't know why I brought that z over, sorry. Wouldn't that give you the top, that would give you the top half of the sphere. If I take the negative of that, it would give me the bottom half of the sphere, right? So we have top half. And then what is my bottom surface? The cone. So I have to solve it for z, but it's already solved for z. So this is z equals square root of x squared plus y squared. Sorry, this is our bottom surface, g of x, y. All right? Now the domain. This part's the tricky part. We have to figure out what the domain is. So we have to imagine shining a light, casting light down, and it would create a shadow, wouldn't it? And that shadow would come down and hit my xy plane, and my shadow would be a circle down here, wouldn't it? But what circle? I mean, we have to know the radius of it, don't we? So we have to figure out where these two intersect one another, right? We have to figure out where these two curves come to get, where these two surfaces hit one another, and that will tell us, right? That will tell us what the radius of that shadow. So let's find the intersection. See, in the last problem, you didn't have to worry about this because the ground was our domain. But here, the ground is not our domain. Otherwise, it would be a point, right? It's not a point. It's the whole shadow. So we set these equal to one another, right? We have to solve them both for z and then set them equal to one another. So just remember, you're setting z equal to z here, that equal to that, solve for z. So you get essentially like 1 minus x squared minus y squared equals that one, square root of x squared plus y squared. And then you can square both sides, and you get this. Y squared. And then let's see, how are we going to get, we know it's a circle, right? Yeah. We just want to know the radius. So let's get it to look like a circle. So we'll move everything to one side except the constants. Now what? We want this to be a circle. X squared plus y squared equals r squared. So divide both sides by 2. So what is the radius? What is the radius of that circle? It's root of 1/2, right? It's the square root of that side, because that side over here is r squared. So it's root 1/2. And you could simplify that, or you could rationalize it, and right, this becomes like 1 over root 2, and if you don't like that, you could write as root 2 over 2. It doesn't matter, right? Those are all the same thing. Okay, so let's take a look at our domain on the ground. Our domain on the ground is going to look like a circle. This is our shadow on the ground, right? And the radius of this is 1 over root 2. Right? That's our radius. And since this is our domain, and it's a circle, we are very happy to employ polar coordinates at this point. So in polar, our restriction on theta is what? 0 to pi. And our restriction on r will be 0 to 1 over root 2. Okay. Now, the next thing we need to do is go back to our two functions and convert them over to polar also. So replace all our x's with r cosine theta, all our y's with r sine theta, blah, 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 right? And I think the same thing happens here as the last problem, right? This right here, when we go to polar, we can pull out the negative. And so when we pull out a negative, we'll have x squared plus y squared, so that'll just be r squared. So this becomes square root of 1 minus r squared. And what does this one become when we go to polar? It's the square root of r squared, which is the absolute value of r, but here we're assuming r is positive because r is positive. So this is just going to be r. Z is r. Here z is this. So we got our two surfaces written in polar form instead. We happy? Double integral, set it all up now. I'm going to go ahead and do my thetas on the outside. 0 to 2 pi. Here, 0 to 1 over root 2. And then what goes inside here? Square root of 1 minus r squared, right? That's the top surface, minus the bottom surface, r, times r, dr d theta. And that's that one right there, right? This is the one. This is that one right there. Told you not to forget, right? Every time you go to polar, you have to put that r in there. Sometimes you're happy to see it, sometimes you're not, because sometimes it can make the problem a lot harder. But this actually might work out pretty nice, because if we distribute that r through here and here, well, this one becomes r squared, right? And that one has an r in front of it like that. And then I can integrate that by itself, no problem, 1/3 r cubed. This one would be just a basic u sub. Right? U is the radicand, and then derivative of that is negative 2r dr, 2r dr. So we'll be able to tweak it and get it to work. I won't continue on that one. I'll just give you the answer. Is that all right with you? Okay, so 0 to 2 pi, 1 over square root of 2. Whoa, whoa, what? Square root of 2. And then we're going to do r times the square root of 1 minus r squared, and then minus r squared. Yeah, dr dt. All right, so we're getting a pretty nasty looking exact answer. That's it right there. So that's the non-approximation exact answer. Now, to get it as a decimal, I just have to take that and take that answer and multiply it times 1.0, and it'll give me the actual. There you go. That's the volume. 0.613434 is the approximate decimal answer for the volume between those two surfaces. Okay? Polar's pretty nice, huh? Really does make a lot of problems that would be very difficult in Cartesian much easier. All right. So let me remind you of something before we do this. Do you remember how when we were in Cartesian, we started off by integrating over rectangles, right? When we were doing our double integrals, we started by doing it over r, and r was a rectangle. And that's what it looked like. And that meant our x's were between two constants and our y's were between two constants, yes? And then we did type 1, where what we said was our region was something like this, where our x's were between two constants, but our y's were between two functions of x, right? That was type 1. And then type 2 is the other way around. Our y's were between two constants and our x's were between two functions of y. Well, when it comes to polar, we have something similar. So in polar, what if I tell you that your theta is between two constants, alpha and beta, okay? So you're only allowed to rotate between alpha and beta, but your radius is no longer between two constants. Your radius is actually a function of theta. So your radius is now, what am I going to use here? H1 of theta and H2 of theta. So now, instead of it looking like this, right, like this, where your theta is between two constants and your radius is between two constants, now your radius here can actually vary depending on the theta itself. And so what you have is an outside border, which is dictated by this function, and then some inside border, which is dictated by some other function. Do y'all see the similarities between that and this type 1 in Cartesian? Do y'all see it? Okay. So before we actually do a problem here, I want us to get some idea of what these things look like. Like, what does a function of theta look like? I mean, how do we write them? So let me do it this way. What if I tell you this? I'm just going to use h instead of h1 and h2. What if I tell you h of theta is equal to theta? What would that look like if I draw it? So remember, this is actually the radius. So the radius is, according to this, I'm saying that the radius is always equal to the what? The angle itself. So let's try and draw this. Yeah, so if I'm pointing out this direction, I always start here, theta is what? 0. And that means my radius is 0. So I put a point here. Now what if I rotate by, let's say, pi over 4? So let's say now I'm pointing out this direction at pi over 4. If I point out that direction, how far do I walk out? Pi over 4. Whatever that is. So let's say I measure whatever pi over 4 is. I walk out that much. There's my point. And then let's say I rotate to pi. How far do I walk out? Pi, which is going to be here, right? Something like that. So if this is pi over 4, that's pi. Right? What if I rotate all the way around? Wait a minute. Did I say pi? I said pi, didn't I?
You said pi.
I said pi. That's not pi. Okay. Rotate to pi over 4, I'm here. Rotate to pi over 2, it's double that, right? So I'm here. Then when I rotate to pi, I walk out pi, which means I'm here. And if I were to do all the angles in between, then it should start to look something like this, right? The bigger the angle gets, the further away I walk. Does that make sense? That's what that looks like. Okay. But there's no restriction on what that function can be. Let me give you another one. What does h of theta equals cosine theta look like? Ooh, okay. So let's try this one. Let's start out. And for this one, I think what I'm going to do is I'm going to bring in a t-table to help us with this. So over here in like a t-table, I'm going to put theta here and then h of theta here, which for us is cosine theta. So let's start out with 0, because if we're pointing out 0, that means we're pointing that way. How far do I walk out? 1, right? Because this is cosine of 0, which is 1. So when I'm pointing out this direction, I walk out 1 unit and I put a dot. Okay, that's at 1. All right, let's go to a different angle. How about pi over 4, which would be pointing there? When I point at pi over 4, I get cosine of pi over 4, which is root 2 over 2. Okay, so that's 1, right? Root 2 over 2 is not as big as 1. It's smaller. So imagine having a little bit smaller, but I'm pointing out this way, so something like that. Is that okay with you? All right, what about, let's go to the next nice angle we know, pi over 2. What's cosine of pi over 2? 0. So that means when I'm pointing straight up, I'm at 0. Now, to get an idea of what's happening in between here, we could do more points, right? Like more values, we could do like pi over 6. Cosine of pi over 6 would be like root 3 over 2. So at pi over 6, you would be like here maybe. And then if I did like pi over 3, what's cosine of pi over 3? 1/2. So I'd walk out 1/2. That would put me like right around here. You'd have to actually like measure these. But trust me when I tell you that this would draw the top half of a circle like this. And it is a circle, all right? And now I keep going. Let's get some other angles. How about this angle right here? What's that angle? 5 pi over 4? Right? Hold on. No, what? I need to go back. I need to take pre-cal again. 3 pi over 4. That's 3 pi over 4, right? What's cosine of 3 pi over 4? It's negative, right? Negative root 2 over 2. So that means when I'm pointing out this direction, I'm supposed to walk backwards root 2 over 2. So instead of walking this way, I walk backwards and I drop a point at root 2 over 2. So I'm gonna be doing something like this. Does that kind of make sense, what I'm doing there? And then I keep doing that, and as I rotate around, let's see, what happens when I get to pi? Pointing out this way. What's cosine of pi?
-1.
You're at -1. So when I'm pointing out this direction, where am I? I walk backwards 1. I'm back to here. So you wind up drawing the bottom half of the circle. So if my theta goes between 0 and pi, I actually draw that circle. That's what that function does. H of theta is cosine theta. Draws that circle over here, right? It draws that circle between theta being between 0 and pi. What happens if I open this up and I say 0 to 2 pi? It's going to repeat itself. It's going to draw the circle on top of itself. All right? It's kind of interesting, right? Draw a circle like that. It is weird. Hey, just out of curiosity, this is a real curiosity here. That circle that we just drew, let me blow it up for you real quick. The circle we just drew, right there. What's the center of that circle? 1/2, right? What's the radius of this circle? 1/2 again, right? Okay, give me the Cartesian formula for that circle.
So like 1 minus square root of 1 minus x squared, or something like that?
Yeah, it's based off of this formula. Remember that formula?
Yeah.
That's the general equation for a circle in two-dimensional space centered at hk with a radius of r. Now, when h and k are 0, you're centered at the origin, aren't you? But h and k can be different numbers. That'll shift you around. So for this, if this point right here, if this is our center, that's the point 1/2, 0, right? So that's h and that's k, isn't it? And the radius we just said was 1/2. So what's the equation? What's the equation of this thing? X minus 1/2 squared plus just y squared equals 1/4, right? Agree? Now why the heck am I showing you this? Why am I showing you this? Because I'm telling you that in polar coordinates, this is the equation of that circle, right? I'm telling you basically that the equation is r is cosine theta. R is equal to cosine theta, right? That's what I'm telling you. But in Cartesian, this is the equation of the circle. So watch this. I'm going to square that. If I square that, I do a little FOIL action there. Okay, that's what I would get when I FOIL that. Plus y squared equals 1/4. With me? Yes? What's that in polar? R squared minus, what's that in polar? R cosine theta equals, now I killed the 1/4, so 0, right? Part?
You're right.
Now, factor out an R, right? Factor an R out and set each of those equal to 0. What, R equals 0 or? That equals 0, which is R is equal to cosine theta. You'll see that? So when you convert this equation to polar, the only way that this equation, that equation, or the only way that you can go from here to polar is if you let R be 0, which wouldn't draw you that circle at all, right? Or R is equal to cosine theta. And that's the way I defined it to begin, right? So there is a way to get from Cartesian to polar. See it? All right. We could spend 3 weeks on polar, on graphing polar functions, and in calculus 2, you may or may not have gotten done calculus in polar coordinates. There's ways to find areas and things like that. I know in my Cal 2 we didn't have time. We ran out of time. We got sequences and series done, but we didn't get to polar. Did anyone do calculus polar? Yeah, you did? Here?
Yeah.
Did you do sequences and series?
Yeah, we did those too.
Really?
We had time for all of it.
Who'd you have? Do you know?
His first name was Steve.
Okay, all right, gotcha. All right, here we go. A sphere, this is a problem I promised you at the very beginning. A sphere of radius 3 has a cylinder of radius 1 drilled out as shown below. Set up the double integral which yields the volume of the remaining solid. So we had this idea that we have this sphere that has a radius of 3, right? And what we want to do is we want to drill out a hole that is offset. See how that hole is offset? We want to drill that hole out with a drill bit that has a radius of 1. Drill it out and then tell me what the volume of this is. Okay? Get the idea? So the way we're going to do it is we're going to try and find the volume of the part we're going to drill out. And the way to see this is to, I think this was it. Let me take all this crap out of here. That green part's the drill bit, but I'm going to take the drill bit out of there. Do you remember me showing you this?
Yeah.
We said we need to find the volume of that piece, but the problem is that the top piece, that top cap right there, has a little bit of a rounded surface to it, right? It's a little rounded. But if we look at this, oh, and also I didn't go all the way through, right? So we're going to just try and find the volume of this and then double it because of symmetry, right? So if you look at this right here, can you see that we have a top surface and a bottom surface?
Yes.
Okay? Do you see that the shadow on the ground is a circle, which means we can use polar? So this is a pretty straightforward idea now. We find the volume of this, we double it. Whatever that is, we subtract it from the volume of a sphere, which we have a formula for, right? So y'all understand the attack on this? All right, so let's get it set up. First thing we're going to do, let's try and draw that little piece we're going to do. So it's kind of like got a little rounded top to it. It's kind of hard to draw that rounded part, and then we got something like that, all right? That's the thing we're looking at. We're going to double whatever that volume is. So let's start with the top cap. The top cap, and then the bottom piece right here. So this as a function of two variables, and then this one as a function of two variables. So what is that top cap made from? The sphere. And the sphere was x squared plus y squared plus z squared was 9?
Yes.
Radius of 3, right? The sphere is a radius of 3. So this top piece is coming from that equation. And when we solve it for z, we get just the positive root, because we're talking just about the top. That's already come up before, right? So we're going to have an easy time converting that over to polar. And then the bottom, this one's easy too, right? That's just the ground. I say it's easy. Is that easy or not? I don't want to put words into your mouth. Okay, what should I look at next? The domain. Well, the only thing that you need to know about this, and I don't think I stressed it enough to you now, or when I first presented it today, but when I presented it originally, I did stress this. What we're doing is we're drilling this thing out, and our drill bit is always going to stay parallel to the z-axis and tangent to the z-axis. So it's like the outside edge of that drill bit will always be touching the z-axis. Yes? Okay. So when we drill out, so what does that look like on my thing here? Well, it could be any circle of radius what?
Radius
1 that touches, that is tangent to the z-axis. Any circle I want. So I could draw a circle that went like this and ran tangent, so long as the radius is 1, right?
Yeah.
But to make things convenient, let's try and position this thing somewhere where we can find the equation of it. Because if I just offset it like this, what's the equation of it? It's going to be hard, right? So what we can do is we can just, let's place it like this. Let's place our drill bit like this. So that this right here is what? Careful. What is it? 2. Because the radius is 1, right? That means the diameter is 2. Is this a polar region? We think so, right? Didn't I just show you one that looked like this a second ago? It was h of theta was cosine theta. But that was a little bit different because this one has a different center, right? What's the center of this circle? 1. What's the radius of this circle? 1. So the equation of this is x minus 1 squared plus y squared equals 1 squared. That's the equation of that circle, right? And now what I'm going to do is I'm going to pop this thing over to polar by doing what I just showed you a second ago. I'm going to expand it all out and then work it. So this will be x squared minus 2x plus 1 plus y squared equals 1. The 1's cancel. X squared plus y squared is r squared. And this piece right there becomes minus 2 cosine, 2r. 2r cosine theta equals 0. Factor out an r. And so we have two possibilities here. R is either 0 or R is equal to 2 cosine theta. Here's one slight little thing we have to consider. If I ask you to sketch this, right? We would start plugging in values of theta. Like when we plug in 0, it would spit out what? So 0 for my angle would spit out 2, right? And then if I plug in another angle, it's going to spit out another point, and then another angle, another point, another angle, another point. When I go straight up, it's going to be here at 0. When I go this way, it's going to start drawing the bottoms, right? But see, I don't want my region, right? My region is not just the outer edge, it's everything in between. So when theta was 0 back here, it was, we don't want to say it's, my radius is 2, we want to say it's everything between 0 and 2. That means it gives me everything in here. And then when I rotate a little bit more, I want to be here, but I want to be everything between 0 and there. And then this point, everything between 0 and there. And then 0 and there. And what will happen is it'll fill this in. As I turn, it's going to fill in. Does that make sense? Because I'm trying to come up with this restriction on theta, restriction on r. So what is my theta going to be between? 0 and pi only, right? Not 2 pi, because 2 pi will draw the circle twice. So my theta is between 0 and pi. Now my radius is between two functions of theta. The first function is 0. It's the 0 radius. And then my second function is the actual circle. That's what I was trying to say here. This right here gives you all these little line segments in between the origin and the outer edge of the circle. And so when you go out backwards, it's going to go like this. Make sense?
When you draw the bottom half, though, aren't your limits reversed?
Your limits would be opposite, wouldn't they?
Yeah.
Yes. Yeah, so that wouldn't make a lot of sense, would it? I mean, when you think about this, once you go past what, pi over 2, then this part becomes negative, doesn't it?
Yeah, so it would be r.
So they would need to be the other way around, right? So this is an important point that needs to be brought up. You're a little ahead of me, but that's okay. I think we can just do it right now. When we go from 0 to pi over 2, right? We go from 0 to pi over 2, everything's going to be perfectly fine. This will make perfect sense. But once we go past pi over 2, what?
Start drawing again.
It's going to start drawing backwards, and this inequality won't make sense. Yes? So how do we resolve that? Okay, so two integrals. Let's think about this. Let's remember what this domain is doing. This domain is these points are being plugged, these are down here, right? And they're being mapped up into this, right? And we're trying to find the volume between these. If I only do this top half, if I were only to do that right there and plug those in, is the other side symmetric?
Yes.
Is it symmetric? I mean, you have to convince yourself of this. So if we look down, let me bring the picture back up here. If I look at this thing right here, or maybe I should look at this one over here too. Look at it from the top like this, so that these are kind of side by side. If I only go and integrate over that bottom domain down there, right there, and bring that up into this, that would only give me the volume of that piece. The other side is symmetric, do you agree? Only because it's a sphere.
Yes.
If this was a plane, then it wouldn't be, and you would have to break it up into two integrals for that to make sense. Does that kind of, So how can we do this then?
We do 0 to pi over 2.
We can change this to 0 to pi over 2 and then double that answer. But then we're going to have to double it again because this was only the top part of the part we drilled out. So really we're going to just multiply everything by 4. It's a little tricky. It gets a little tricky. All right, let's go for this. Let's try and set up this integral. Can we get these functions over to polar? This one into polar is just root 9 minus r squared. So I think I'm ready for my double integral. Y'all want to go ahead and just get the whole thing now? Just 4 times, yeah? Okay, so I'm going 4 times the double integral, 0 to pi over 2, and then what? 0 to 2 cosine theta, right? And then what?
Root 9 minus r squared.
Root 9 minus r squared minus 0, right? Because the bottom is nothing. And then we have to bring the r in. So let me throw the r out front. And then dr d theta. Nope, theta's on the outside. Right, theta's 0 to pi over 2. And then that means, so now we no longer have the freedom to change those.
Theta's always going to be on the outside.
If theta's between the constants. So that would be it right there. So let me do this one. 4 times 0 to, integral 0 to pi over 2, and then 0 to 2 cosine theta, right? 2 cos t. And then we're doing r square root of 9 minus r squared, and this part's not here. That look good? 4, 0 pi over 2, 0, 2. I think that looks good. Yes?
How can we switch the domain for theta from pi to pi? Or pi over 2?
Why did I go pi over 2?
Yes.
Okay, so let me go back to when we were drawing this circle. When we draw this circle using this right here, if theta is 0 up to, then I go out to this point. If theta is pi over 4, I'm going to draw a point here. If theta is like pi over 3, I'm going to be like here. If theta is pi over 2, which is straight up, I'm going to be here. So when you're between 0 and pi over 2, you draw this first half of the circle, right? And what we're saying is to make it a solid region, what I need to say is that my radius is between 0 and that point. So from 0 to here would be that. Turn a little bit. Next thing, next thing, next thing, next thing, next thing, next thing. Here's the problem. When we get over here, like to let's say there, now you're saying what is cosine of 3 pi over 4, which is negative root 2 over 2. So I can't say now that my radius must be between this because there is no radius that is smaller than a negative number and bigger than 0. This inequality is backwards now, right? So to save ourselves, we are just going to look from here to pi over 2 and then double it because the other side, fortunately, it's not that the other side is symmetric. That's not the important part. The fact that the surface above it is symmetric, okay? Because if this part up here didn't have symmetry, then you couldn't do it. So then you'd have to break it into 2 integrals, and then you would have to somehow make this go backwards. So you would basically like flip the inequality and run it. But see, here's the thing. Cosine is an even function, so it's going to wind up working either way. But let's get this as a number, because obviously the computer is using some elliptic functions to get an answer, and we don't want that. We want a numerical answer. That's what we want. So there we go. The volume that we drilled out, right? The volume that we drilled out is 17.1639 whatever, cubic feet, cubic inches, depending on the ball itself. That's what we drilled out. So we still need to figure out what the volume of the actual ball was. What was the volume of the ball? Well, we used the formula, what is it, 4/3 pi r cubed? Isn't that the formula for the volume of a ball? Or the volume of a sphere? Yes? Okay, so